Okay, so today our speaker is Jon Carlson, and he will be giving talk on idempotent modules and endomorphism. And
Very good, thank you. Okay, well, thanks for inviting me for this, and I'm actually giving a talk that I gave in a seminar on new trends in triangulated categories and group theory a few weeks ago. If you all were here last fall, that is a year ago fall, you heard the first part of this. But since it's probably unreasonable to expect you to remember it all, I will actually begin by reviewing what we did. So this is sort of a sequel to what I was talking about a year and a half ago. I'll talk more about this, but at the time, when I gave this talk in Oberwolfach, I had made the statement that I thought I could generalize it. And that turned out to be more difficult than it's still, the answer is yes, I can, but it turned out to be more difficult than I thought. So that's sort of what this is all about. At any rate, let's start here. Let's see. Okay, how do we do this? No, that doesn't work.
I think it will work now.
Oh, okay. There we go. All right. So here are the players. K is going to be a field of characteristic P. And we want it to be reasonably large, but so let's say algebraically closed. G is a finite group, perhaps a group scheme, but we'll talk about that some too. So mod KG is a category of finitely generated KG modules and capital MOD KG, the category of all KG modules. We have a dual, I'm not sure we're going to use that much. There's also a tensor product, which we will use. And in the case where you're talking about a group algebra, the tensor product, this is a tensor product over the base field K. And it's made into a KG module for the group algebra by using this diagonal structure that G times M tensor N is GM times GN. For if you're using a different group scheme, you probably have a different Hopf algebra structure on this, but these are Hopf algebras, so this is what we want. Okay, just some notation. If you've got a KG module M, you take a projective resolution, projective cover. The kernel is what we call omega of M, and inductively you can repeat this. So these omegas turn out to be sort of the terms in a projective resolution, not the terms, but the images of the boundary maps in a projective resolution. You can also do an injective resolution. We call this omega inverse. And we can get away with all this because this is a self-injective ring. Projective modules are injective and vice versa. So we get away with all that. There is a calculus of these things, but I don't think that's going to be important for what we want to do. Okay, stable category. Okay, so and if you're doing cohomology or anything like that, that ignores projective and injective modules, which are the same in this case. And so we generally try to work in the stable category. The stable category has the same objects as the module category. It's just that the morphisms are different. What we do is we factor out any morphism that factors through a projective module. And so, so as I say, this gives us a stable category. And we can do a stable category of finitely generated modules, which we call little StMod kg, or the category of all kg modules, which is the big StMod kg. And the point is that these are tensor triangulated categories. Categories correspond more or less to exact sequences. And the shift functor is this omega inverse. So when I say this is a triangle, what it means is you go around the triangle, you go L to M to N, and then the next step is you go back to L, but you have to shift by omega inverse. This corresponds to an exact sequence. That is to say, if we add a projective module to M so that the map from L becomes injective, and then map it onto N, then you actually get a short exact sequence out of this. And we will talk about that some more too. Okay, support varieties. All right, cohomological variety is the projectivized prime ideal spectrum. In other words, it is the collection of homogeneous prime ideals for the cohomology ring. Okay. Now let me just say this cohomology ring H star GK is a nice finitely generated K algebra. In the case that G is an elementary abelian group, meaning it's a direct product of cyclic groups of order P. This cohomology ring is essentially, that is modulo its radical, it is a polynomial ring. So in that particular case, what this V sub G of K is just a projective space it would be P sub R minus 1, where R is the number of direct factors in G as a product of cyclic groups of order P. For a finitely generated module, we can define the support variety. It's a closed set of all homogeneous primes in V sub G of K, that contain the annihilator of this algebra X star MM. If M is finitely generated, then this X star MM here is actually a finite dimensional algebra, finitely generated algebra over the cohomology ring. And so this all makes sense. For infinitely generated modules, this gets a little bit more complicated. In the context that I'm working with today, the way to think about some of these things is through something called pi points. This was a notion that Eric Friedlander and Julia Pavsova came up with a few years ago, sort of extending results that I and several others had worked on to general finite group schemes, but this actually works pretty well. So first of all, what is a pi point? Well, it's a map. First of all, you extend the field K to little k to capital K. You look at this algebra, KT mod T to the P. This is the group algebra of a cyclic group of order P. You want a flat map of that into KG. Flat means that if you look as KG as an algebra, as a module over KT mod T to the P, then it's a projective module. That's what flat means for you. These things are called pi points. And the set of equivalence classes of pi points is homeomorphic to, and here's a misprint, I'm sorry, is homeomorphic to V sub G of K. That is the actual spectrum itself. The way you get this basically is if you take one of these pi points and you pull back the cohomology ring, the kernel of that, the cohomology ring of this thing is basically a polynomial ring in one variable. If you pull back that cohomology, then the kernel of that thing is going to be a homogeneous prime ideal. And that's where you get the correspondence. Because we're allowing extensions here, we can actually have a notion of specialization, so that we can specialize one pi point to another. The specialization topology that you get from that is actually the same as the topology that you get from the spectrum. Okay, so this is why we say that it's homeomorphic. So these are spaces and with a topology, and there's a homeomorphism between them. Okay, so if I've got a module M, and M can be infinitely generated now, the variety of M is actually the collection of all alpha, such that this, when I pull back along this pi point, I get something that is not projective. And so because we're allowing extensions, by the way, this alpha it corresponds to a point in the cohomology spectrum. But that may be a generic point, because I'm allowing a generic point for some irreducible subvariety, because I am allowing this extension of fields. Okay, and we say that two pi points are equivalent if they measure projectivity the same way. In other words, a module is projective for one if and only if it's projective on restriction to the other. Okay, now here's the categories. Subcategory of M and StMod KG is thick, provided it's triangulated, so with the same triangles, and closed under taking direct subsets. It's a thick tensor ideal if it's also closed under tensor product with arbitrary finitely generated modules. So this is the notion of thick tensor ideal. There's a theorem here. BCR is Dave Benson, myself, and Jeremy Rickard. It says if M is a thick tensor ideal in StMod KG, then in fact there exists a collection of subvarieties of V sub G of K, which is closed under specialization of finite union, such that this thick tensor ideal is precisely the set of all modules. Its objects are precisely the set of all modules whose support variety is in this collection. Okay, so in other words, the thick tensor ideals are determined by collections of subvarieties of the spectrum of the cohomology ring that are closed under specialization and finite unions. Okay, Rickert proved this. Okay, he said given M and V, as in the theorem, then there's this distinguished triangle where this EV and FV are idempotent modules. This is sufficiently, we're going to use this enough. Let me actually write it on the blackboard. Okay, so we got a triangle, EV goes to K, goes to FV, okay? So this is a triangle in the stable category. What happens is that this EV is has exactly as the support variety exactly equal to this set V. And FV has it precisely the opposite. It's the V sub G of K minus that set. Okay, and these things also have some universal properties, which I'm not going to go into in great generality. But this is a really important notion, and this is what really I'm talking about today. Here's the thing. We got a thick subcategory of the triangulated category S in general. The Verdier localization. I mean, the whole point of thick subcategories, by the way, is that you can localize with respect to these. You get a new category out of this. And the whole point of thick tensor ideals is that when you do that localization, what you get is something that still has the tensor product structure on it. Okay, so if you've got a thick tensor ideal, thick subcategory, closed under taking direct summands, the Vernier localization is a category whose objects is the same, but whose morphisms are obtained by inverting any morphism if the third object of the triangle is in the subcategory. So what this means is that if I've got unfortunately, I wrote this from left to right. If I've got a morphism from L to M, then what I can do is I can take any ordinary homomorphism, and then I invert anything if the third object in the triangle is in the subcategory. In other words, it's going to look like gamma theta inverse, where theta has a map with that's the third object in the triangle of that morphism is in the category M. So this is sort of the general notion of this. If you read Balmer and Fabi, by the way, they talk about something called the Ballsfield localization, which is more specific. The difference between the two is some subtle thing that I'm not sure that I understand. But at any rate, I think in the case that we're talking about here, they're really the same. Okay, so this is what the localization is. So I want to go back to one of these things where we're looking at a subcategory determined by of all modules with variety in a certain subset of the ideals. And I want to do the localization here. And the point is that this tensor with this f of v is the localization functor. And the whole reason is because if you go back to this triangle, this E of v that we had has support variety in that subcategory. So it's going to be sort of 0 in the subcategory. And so this basically what we're doing is we're sort of inverting this morphism. It's a little more, that's sort of the basic idea. So tensoring with f of v is this localization functor. So in particular, what this does is it identifies k with f of v. And tensoring with f of v actually sends the category of finitely generated KG modules into the category of all KG modules. These E of v and f of v are not necessarily finitely generated. In fact, it will be very seldom that they're finitely generated. So you're going into the category of all KG modules, but the image of that is actually the localized category. The image of that functor is actually the localized category. And so the question is, what is this f of v? Now, as I say, the endomorphism ring of K in the localized category is the same as the endomorphism ring of f of v in the stable category. And the stable category, I sort of know what I'm doing, or I think I do. And so actually you can think about actually computing that in that particular case. Okay, so this is where we were last year. Let me just point out a couple things. So one example, if I take an element just at any non-nilpotent element of degree d in the cohomology ring, and I let V be the variety of all prime ideals that contain this element, then this M of V is a thick tensor ideal, again, consists of all KG modules with V sub G of M and V. And in this case, I can tell you what the endomorphism ring of K is in the quotient category. What you do is you invert zeta. because the third object in the triangle of zeta is going to be in that subcategory. And then what you have to do is you have to take the zero grading. Because zeta is homogeneous, you still have a graded ring. And so you take the zero grading. And that's what you get. And this is something that we've known for a long time, okay? In fact, I think I even say this. Yeah, this was in Jeremy Ricketts' paper, but in some sense, we knew this even before that, or knew something like this. But what I realized, this is a very special case. This is just taking one generator for the ideal. Suppose you take two generators for the ideal. Well, it's sort of clear that the same thing was not going to happen again. And that's why I was interested in doing this project, was to actually figure out what happened in these other cases. Okay. So for a few minutes here, anyway, I'm going to assume that P is equal to 2, because what I write down is actually much easier to deal with in this case. I can do a similar thing in odd characteristic cases, but it's more complicated. Okay, I want to look at a group of this form where it's H cross C, where C, so it's a direct product of two groups, where C is a cyclic group of order 2. I want to let V be the image of the under the restriction map of the spectrum of the cohomology ring for C. And this is a closed point in V sub G of K. Okay. And then I want to actually write down what these two modules E of V and F of V are in this triangle. Okay. So how do we do that? Let's see. Well, this is what it looks like. I'm going to take a projective resolution. This is a KH projective resolution, where H is this direct factor of G. I really want it to be a minimal projective resolution, but that's okay. Take a projective resolution. Then I can write down what these things look like. What this F of V is, restricted to H, it is the sum of the terms of the augmented projective resolution. Okay, so that's what it is restricted to H. I make it into a KG module. Well, all I have to do is say what the actual Z is. Well, Z is this thing whose square is 0. Okay, but you know, if you take the boundary map and you square it, boundary is 0. This is the complex, the projective resolution. So all I'm going to do is I'm going to let Z act on this thing basically by the boundary map. Okay, and then that's on F of V. On E of V, you do the same thing, only I don't have the K. Turns out that this is exactly what you want. It takes a little bit of proof to get this, but that's the idea. So I'm getting this F of V and E of V by just taking the sums of the terms in this projective resolution. In the case of F of V, I needed the augmented projective resolution. Okay. And when P is odd, by the way, you can do this, but what you have to do is you have to take sort of every other term and add a multiplicity here, add it P minus 1 times. And that's, the notation gets a little more complicated than you want to see. Now, we're going back to this localized category. What we said was that in the localized category, K becomes identified with F of V. So actually what I've got is isomorphism, where Hom of K in the homomorphism, endomorphism ring of K in the localized category is a map from F of V to F of V in the main category. or maps from K to f of v, again, in the stable category. So I know what f of v is. I can figure out what maps from K to f of v is. It's basically, I mean, if I go back to what my f of v is, it's the sum of these terms, so it's going to be a map from K into the bottom of these things. So I know what these are. I want to make this identification, and I want to say what happens. So in the localized category, which is now I'm going to use everything, all KG modules mod M. An endomorphism K is equivalent to one of this form. Okay, we just remember what we were doing here. We're going to invert anything if the third object in the triangle is in the subcategory, which means basically, I'm going to, I think I call this beta, I'm going to invert that map. Okay, and it turns out that I can get then every morphism from K to K by taking mu and then the inverse of beta. And mu has to be a map from K into these p subbands or into K itself, you know, into this f of v. All right.
Should we not be clean up, bro?
Hello?
Sorry.
Lisa? Yeah, okay. Okay. All right, but here's what happens when you do this. If you've got a map from K into the projective resolution, a KH homomorphism, then that in fact is the Tate cohomology ring, the negative Tate cohomology ring, or let's say non-positive Tate cohomology ring. So what happens is that the endomorphism rings of K is in fact equal to this. And with a lot of work, well, not too much work, but some work, what you get, in fact, that this is not just an isomorphism of spaces, but it's also an isomorphism of rings. Okay. All right. Okay. So here's what we've got. In characteristic P, we do the same thing. We can do the same thing. You get this isomorphism of rings between the endomorphism ring of K and this negative Tate cohomology ring. Okay. If H is an element of two consequences of this are if H is an elementary abelian P group of rank 2 or more, then this endomorphism ring is infinitely generated local ring whose radical has square 0. This actually comes from a paper that Dave Benson and I wrote 30 years ago or so on negative cohomology. Okay, and if H is any finite group, P rank 2 or more, then this endomorphism ring of the trivial module, it's going to be an infinitely generated local ring. It's a huge ring, but it has very few products in the negative case that are not actually 0. That is that in this, it has this radical, which is the actual negative stuff, and that's going to be basically almost all products in that negative part are 0. And as I say, this stuff has been known for close to 30 years now. Okay. So here's what we want to do. All right. So what I've showed you was the sort of stuff where we were up to I was up to about a year and a half ago, something like that. So yeah.
Can you back up just one slide?
Sure.
So for finite group schemes, can you actually deduce the same result?
Yes, this actually works for finite group schemes. Okay, so far. All right. And what the next part I do will also work for finite group schemes, but then at some point we're going to lose that, unfortunately. Okay. Okay, so so what I want to do, and by the way, this paper has actually been accepted now after being a year or so with the referee. One is happy when it finally comes through, I guess, you know. Okay, so I want to get this slightly more general. I would actually like to do this for any subvariety V of code of dimension 0. Okay, and for any finite group. Okay, the first step that you have to do is to actually do it in the case of that G is an elementary abelian group and has rank at least 3. That is to say, what we've done up to this point is we've done it in the case where V is a single point. Dimension 0 means it's going to be I actually want a finite collection of points. So I've done it in the case where V is a single point. Now I want to do it in the case where V is a finite collection of points. This is the extension that I want to do. I keep feeling that this ought to be easy, you know. It turned out to be much more difficult than I had anticipated.
So V of G is already projectivized. Is that what you're saying? You think of it as,
The V of G is the projectivized prime ideal spectrum.
so you project that. Okay.
Right. So V is a point in there, which means it's a line in the affine, if you want to think of it that way. Okay. Okay, so as I say, the first step is to go with the G and elementary abelian P group. As I say, I kept thinking that this ought to be really, really easy to do. It's not, or at least I haven't been able to figure out an easy way to do it. First thing you want to do is we're going, as I say, from the 1-point case to several point cases, which means that V is going to be a union of several 1 points, subvarieties. So you'd like to know what this f of V looks like in that particular case. That is when you've got V as the union of 2 subvarieties, closed subvarieties, intersection 0, different points in this particular case. Then what's f of V? Well, it's actually a push-out. This is not hard to say. The point is that because E of V is a union of 2 things, E of V is actually going to decompose into 2 subvarieties. So it's a push out, which means what? It means that what you do is you take the direct sum of f of V1 and f of V2, and you factor out, you identify the images of K. Okay, standard push out diagram. So this is great. Okay, so we can actually say what it looks like. We need to remember that we're making this identification. Okay, because this is the way we sort of handle things. And this is the proposition that you have to prove, or at least that I think you have to prove. That is to say, we can say what happens here. This f of V was the sum of these projective pieces, the projective pieces of the projective resolution. We want to extend that. We need to extend that to what happens when we're doing f of V of f of V. In order to do that, I actually have to lift K to a chain map on the projective resolutions that I was dealing with. And as I say, the thing is, you assume that K is sufficiently large. You take any alpha to be a pi point that does not correspond to a point of V. You let X be this alpha of T. Now, X is going to have to be a nilpotent operator. it's got to have order p. If I raise x to the pth power, I get 0. It's in the radical of kj. I assume that I've got one of these thetas in f of v, so that's going to be an element in here. That's what I want. And I suppose that it maps the one element in K to an element that's in the projective part of that complex, which means it's in x to the p minus 1 times f of v. What I actually have to show, or seem to have to show, is that the image, that when I raise that to a chain map, when I go from this expression to this expression, that the entire chain map is contained in, entire image of the chain map is contained in this x to the p minus 1 f of v. The importance of this is, as I say, this fx to the p minus 1, that's a nilpotent operator. Its square is 0. So when I compose two of these, I'm going to be multiplying by x to the p minus 1 twice, and I've got to get 0. That is what's got to happen in those particular cases. And so the theorem that we get out of this, K algebraically closed, we want it to be big at any rate. G be an elementary abelian group rank at least 3, and we suppose that alpha is a pi point that does not correspond to a point in V. You let x be this x alpha. And you let this thing be the set of all classes theta, where theta of 1 is contained in there. Then this is, I think, an I. Okay, then what is I? It turns out to be a maximal two-sided ideal in the endomorphism ring of the trivial module, or the endomorphism ring of f of v. It's a maximal two-sided ideal, and its square is 0. And that's because the whole thing has to lift to something whose image is in the product of x to the p minus 1 with f of v. And if you do that twice, you get 0. So that's what you get in the elementary abelian case. And so now what you want to do is you want to lift it to the entire group G. And so we say, suppose that G is a finite group with the property that all of its maximal elementary abelian P subgroups have rank at least 3. That's a constriction that I don't particularly like. I'd like to know a little bit better what happens, but let's assume that for now. Let V be any closed by subvarieties, union or collection of closed sets, finite collection. Pick an idempotent module. Let FV be the idempotent module. Then this thing is a local ring whose maximal ideal is nilpotent. Okay. Not only that, but we can say something about the nilpotence degree. And in order to make this lift, basically what you have to do is you have to use a theorem that, or something like a theorem that I wrote about 20 years ago, that says that that if you've got a set of elements, set of homomorphisms, and if these things vanish on restriction, that is factored through projectives, on restriction to all elementary abelian subgroups, then the composition will be 0 or factored through a projective. If you've got enough of them, and enough of them means that there's this number B depending upon that, depending upon only G and P that will guarantee that. Okay. And so the important thing about this is if you've got an elementary abelian P subgroup, but again with P rank at least 3, and if you take the inverse image of the restriction map from G to E, then the restriction is you can get that. You can get that this is isomorphic to f of v prime. And the ideal I, this ideal I that we're looking at is actually just the ideal of that you would get of the kernel of that restriction, basically. And in particular, it's independent of E. You get this ideal I by this method. You restrict to an elementary abelian subgroup of P rank at least 3. And you look at the stuff that goes to the ideal in that particular case. Okay, so it's independent of the choice of E.
Sorry, so this theorem does use finite groups or not?
This uses finite groups. Yes, I mean the theorem does.
Okay, so
I mean, and that's because you've got to have Serre's theorem like this. The cohomology depends upon restriction to finite groups.
so do you anticipate something like that this being true also for the finite group?
Oh, I'd like to think so. Yeah, but it's going to have to, you don't have the elementary abelian subgroup, so you've got to have some other means of doing that.
But you could replace it.
You need to replace the elementary abelian subgroups with something else. Okay. There's another question that we might ask, and that is whether or not, this is finite generation question, whether or not the endomorphism ring of any module or any HOM actually is actually a finitely generated module over the endomorphism ring of the trivial module. It's certainly a module over the endomorphism ring of the trivial module. This is in the localized categories. Okay. So this is a question that we want to ask. And so as I say, when is the endomorphism ring of a module equal a finitely generated over the endomorphism ring of the trivial module? And it actually really only applies to compact objects, that is elements of that is finitely generated modules. It's obviously true if the support variety is either contained in V or disjoint from V. And that's because when you tensor with either one of these, you're going to get just a finitely generated module back. But the question is, when you do this in the localized category, basically what you're doing is tensoring with f of v, and you may get an infinitely generated module. So what about the other cases? And what happens is, I show this by example, is that the answer is more or less similar to what happens above. I mean, let's go back to this case where we take a non-nilpotent element in the cohomology ring. Let V sub G, V be the collection of homogeneous prime ideals that contain that non-nilpotent element. And let CV be the localized category. Then what happens is this: you can prove a lemma that says, suppose that M and N are finitely generated modules, then the way I compute the HOM in the stable category, in the localized category, is the same way that I did it before. I'm going to take the X from M to N. I'm going to invert the cohomology ring of G acts on this. I'm going to invert this zeta again. I get a graded ring, and I'm going to take the zero grade. So it's more or less the same thing that you did before. Just to show you how some of this stuff works, let me give you a real quick proof of this. Okay, so this is what we want to prove, and here's the way you do it. Let's suppose that we have a morphism. So I've got a morphism from M to N So that means I go from M to L and from L to N. And the map from M to L is the inverse of a map from L to M, inverse of a map that has the property that the third object in the triangle of that map is in the subcategory that you want. And what you have to prove, and this is actually not too hard, but don't have time to really do it yet, is what you have to prove is that for n sufficiently large, some power of zeta annihilates the cohomology of this third object in that triangle. Okay, so then we get a diagram like we have here. Now, zeta to the nth power annihilates the cohomology of x. So what happens when I do this, when I come down by zeta to the n and multiply by gamma, is I've got to get the zero map. Consequently, I get a map theta, which goes here. All right. Now, there's something that's still to prove. What I want to prove is that the third object in the triangle of theta is also in the subcategory. So what we get is, okay, I can come down here and I can put in theta inverse here. The new theta inverse is the mu inverse theta inverse is equal to zeta to the n. So what I'm going to get is I'm going to get nu times theta times zeta to the minus n. And that's what we're doing. That's what we're doing up here. I'm inverting zeta, so I can do a zeta to the minus n. And I multiply by this new theta. And that's an element of the cohomology of an x. So this is how you prove something like that. Let's see. Okay. So what you get out of this is that if I take zeta, if I do this kind of calculation, and I want to know whether or not HOM MN is finitely generated over the endomorphism of the trivial module, this is in the localized category, then it is in this particular case. And the reason is basically is this XMN is finitely generated over XKK. And in both cases, to do the computation, I'm inverting zeta, and I'm taking this homogeneous localization of the ring. So that's basically the way this works. So it works in this particular case. By contrast, suppose we've got a closed subvariety of an elementary abelian P group E, and all I need is that this elementary abelian P group has order P cubed, and that E has a subgroup of order P squared, such that the restriction along the subgroup is not zero. So then in this particular case, I'm going to let M be the induced module. The trivial module on F induced up to G. This is a KF module. Oh, I start with a KF module, I get a KG module. This is not finitely generated as a module over this endomorphism ring. So there are cases where you do not get the right thing, do not get finite generation. And the idea of the proof is really based on the fact that if G is an elementary abelian P group of rank at least 3, take a finite set of closed set points, F proper subgroup, then any element of the idea is basically that if you've got elementary abelian groups, then when you do restriction along of negative cohomology in the elementary abelian groups, that the restrictions all vanish. Okay, so it basically comes down to this. Let's see, I don't see. Yeah. So we get rid of that. Okay, so at any rate, if you've got, that's basically what it is if you restrict negative cohomology in elementary abelian groups, then you always get 0. And if you look at the action of N of the endomorphism ring of the trivial module on the endomorphism ring of M, it actually by something called the Ekman-Shapiro lemma that it goes through a restriction down to F. But this restriction down to F factors through the restriction down to E. And again, you're talking about negative cohomology. And so what happens is that you get 0. You get 0 action of that big ideal on the cohomology ring of this module in the localized category. Okay. How much time do I have? Or am I out of time? Okay, let me,
I have a question.
yeah.
So is there a class of modules for which you can say that NV or NCV finally
Yeah, I mean, there is. If you take it, but my conjecture is that in a sufficiently complicated case,
Yes.
like where the ideal is where the variety is the ideal of something that's generated by more than one element, as codimension 2, say,
Yeah.
that this is that you're going to get finite generation only if the module is either contained in that subcategory, or its support variety is actually disjoint from the support variety, from the variety that defines the thing. I think that's the only case that this is going to happen. I don't know how to prove that yet, but
So, yeah, so you suspect that, I mean, do you plug in the trivial one?
yes.
Yeah.
And the trivial module, it's not finitely generated, but
It's not.
well, oh yeah. Well, I guess it's, I see, yes. Yeah, it's going to be complicated. There's probably more to it than that. Yeah. Okay. Let me just take a minute and I'll just go through this, say this real quick. So this is completely different. There are lots of idempotent modules. One way you can get them is to just take a countable direct sum of the trivial module. It's infinitely generated. But when I tensor the trivial module with itself, I just get the trivial module back. So it's idempotent in the sense that countable times countable is countable, that's the reason. But the idempotent modules that you get in these triangles like this have a very special property. And that is given any pi point, if I restrict along that pi point, one of these has one property. I mean, if I restrict this triangle, what am I going to get? I'm either going to get an isomorphism here, I'm going to get an isomorphism here. So it's always isomorphic to either K or 0. So it's finitely generated. So it suggests another subcategory. Take all KG modules whose restricted to a pi point is compact, meaning finite dimensional, modulo projectives. Okay, this is a fairly large subcategory. It contains all of these idempotent modules, but it's certainly not everything. It's not closed under arbitrary coproducts, for example, because that would give you infinite things when you would do this restriction. So it almost suggests as I say, you can then use this to define other subcategories. In other words, if I've got a subset of points, I can take the full subcategory of all KG modules that have the property that when I restrict to a pi point, corresponding to something in that set, then that restriction is a compact object. This is a nice thick subcategory of KG module. And that in turn suggests new support variety. That is for KG modules. Let me take the collection of all points in here with the property that if I have any 5 points associated to this, then the restriction is isomorphic to finite dimensional or something like that. This is I call this a new support varieties. Paul Ballmer suggested that this should be called something like a locus of compactness or something like that for the module. It's So as I say, you can define the support variety like this, collection of all points with that. Any subset like this defines a thick subcategory again. It does have one unusual property, which I will point out. And that is if I've got a triangle, then the intersection of this U thing of M and N is contained in the support, whatever you call it, locus of the M in the one in the middle. This is sort of the opposite of what you get with the regular support variety, which says that this one is the U sub G, V sub G of M is contained in the union of V sub G of L and V sub G of U. So it's the other thing. There is one interesting case, by the way, where you do this. If you go to a restricted developing algebra of a restricted PLE algebra, this has a nice property that there's a distinguished set of pi points that are actually maps of hop maps. So you can actually compute restrictions along there. These are hop algebra structures, and so you get. So what you get is restrictions along these sub-hop algebras. Well, it commutes with the action of the group. So or with tensor products, I should say. Okay. So I'll just leave you with this. There are two problems that I wish I could answer, but I can't. And that is what we don't know is, in general, is if we've got equivalent pi points, then if I restrict along one and get a compact object, it's the same true if I restrict along another. And I don't know what happens if you have a general. If this thing has a general tensor product now. So at any rate, I'm over. Thank you very much. I'll stop there.
Is there any question for the speaker?
So what happens when UG is?
What now?
So we take a module and then we know that it's M. UG of M is M.
If UG of M is empty, I'm not sure. I mean, this is a good question. I really don't know the answer to that. I mean, these are not questions really about categories. They're really linear questions. You come right down to it.
I mean, I guess my question is certain variant. I mean, what is it measure?
Yeah, it has some nice properties, but there are some things that we just can't answer yet.
Any other question?
Is it always true that these endomorphism rings of M are always modules over the endomorphisms of J?
Yes.
It just may not be.
Yes, that's pretty easy. Yeah.
Any other question? Okay, so if not, then let's thank the speaker again.